Yes.
All right, let's get started. So this week, or I guess today, we were supposed to be doing chemical reactions as our lab, but we're going to be pushing that to next week, and there's a big reason for that. So I have important dates for you guys to write down. So tomorrow, Wednesday, um, your practice exam is going to be going up, and I believe on Saturday, the exam itself will be opening, and you guys have, I believe, 1 week. So yeah. So on tomorrow, practice exam is up, and then Saturday, the real exam goes up, and then you guys will have until the following Saturday to finish it. So the reason why we're pushing chemical reactions to next week is because a big portion of your exam is going to be dedicated to nomenclature, and that's what we're going to be working on today. So for today, we're not going to be using the lab kit. This is going to be a dry lab. So it's just pencil and paper. It's more or less a worksheet. And it's going to be like a pseudo lecture today, as I'm going to be explaining to you guys the rules of nomenclature and how to properly understand it. So, any questions? Okay. So for today's lab, go to modules, and then it's this one, Lab 9, Nomenclature and Writing Equations. And when you open it, this should look, it should look like this. So a couple things I recommend to have in front of you for this is your handout, your packet. This should have been provided to you as you were able to use it during the exam. As this page, common polyatomics, and the periodic table itself is going to be important for today. So I'm going to teach you guys how to properly name chemical compounds. We'll go through a few examples for each rule, and then I'll let you guys go. So, you guys ready to get started? All right. I should, I guess I should start off with, do you guys know anything about chemical nomenclature? Has Dr. Henry like mentioned it in the lecture, or has it been touched on in the homework? Okay. So, part one is ionic compounds. So, have you guys heard of the phrase ionic compounds? Or is it new to you? So ionic compounds, at its most basic definition, it means A compound that is made up of one metal and one nonmetal. So one example of this could be something like one of the most common ionic compounds, NaCl or sodium chloride. So one of the rules for naming ionic compounds is that the structure or the compound, when naming it, it's going to end in IDE. So let's take our common salt here. Give it a name, sodium chloride. So if we look at the chloride itself and we pull up the periodic table, I guess you can't really see it here. We see that chlorine is changed to chloride. So we drop the INE for IDE. Think of this IDE as a period. You know, in a sentence, a period represents stop. This is that same concept. Pretty simple. So let's take one from your uh, sheet here. I know some of these look crazy, but we'll get there. Let's take a look at number 8. CrF3. So can you guys go on your periodic table and find what these two elements are? And then let me know what they are. So what's CR? What element is that? It's chromium. So and then F is fluorine. So one interesting thing about this one is that chromium is actually a transitional metal. So transitional metals are metals that are located in the middle of the periodic table. So this giant red block, those are transitional metals, and those are going to behave a little differently. So the transitional metals, we have to take into account the charge of the element. So we know fluorine is what charge? 1 charge. And we have 3 of them. And we have a single chromium here. We need to balance the charges out so that they equal 0. So what charge would chromium be if we have 3 negative? Three positive. So knowing what we know, we can name it. Oh wait, there's one more rule. I'm getting ahead of myself. We have to know Roman prefixes, or Roman numerals, I mean. So we know 1 is 1, 2 is flat, so on and so forth. So chromium is going to be using one of these Roman numerals, and that applies to all transitional metals. So when you see a transitional metal in the bond, remember that we are going to be using a Roman numeral. Now, one thing a lot of students get confused on is Roman numerals represent charges. A lot of students want to use Roman numerals as a quantity, and that's not correct. So we have chromium here and a charge of 3. A lot of students would want to say chromium 1 fluoride, but that indicates that chromium has a 1 charge, and that's not true. So what we really want to write is chromium 3 fluoride. So that's how we would name this one. You guys have questions about this so far? Am I moving too fast? Okay, let's keep at it. I'm gonna clear the screen. So let's try another ionic compound, but we'll try something simple. Let's take lithium and fluorine. So again, we know it's ionic because lithium is a metal and fluorine is a nonmetal. One metal and one nonmetal is going to give us an ionic compound. So knowing that, how would we name this one? Lithium fluoride. So remember, IED means stop. If you were to say lithium fluorine, it would be considered wrong. So if this was an exam and you put lithium fluorine, it would be marked. So remember, with nomenclature, IDE. E. Yeah, IDE. Until we introduce polyatomics, where this rule's thrown out the window. But we'll get there when we get there. So let's try another one. How about Mg3 and 2? So what's Mg? What element is Mg? Take a guess. It's manganese. I'm kidding. It's actually magnesium. Students tend to get manganese and magnesium mixed together. So something to keep in mind. And N is nitrogen. So one thing to know about ionics is that if we don't take into account how many there are, and I need you to keep that in your mind for when we get into the next part, which is covalence. But just know when we have a metal and a non-metal, don't take into account how many they are when it comes to naming. So magnesium nitride would be the final answer. So let's go to covalence since we have that rule fresh in our head. So one thing that makes covalence different than ionics is that covalents are actually two nonmetals bonding. So if we look at our problems here to the left, we notice that no metals are present. A rule that carries over from ionic bonds is that we are still ending in IDE. However, we're now introducing prefixes. Bear with me, I'm writing with my mouse. So 1 is equal to mono. 2 is di. 3 is tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. And 10 is, oops, 10 is deca. So you're gonna need to write these down. I recommend writing them down on the packet if you printed it out. That way they're always there. You can always flip it back and forth to that. Um, but yes, these are very important for covalent bonds. So let's take a look at something simple here, like SO2. Actually, I meant to put CO2. So, what are our two elements here? Carbon and we have oxygen. So, knowing what we know that IDE is going to stop. So we're dropping the GEN for IDE or the Y as well. So we have carbon and oxide. However, we're not done. So prefixes, unlike transitional metals, is based off quantity. So we see this too here on the oxygen. That means there are two oxygens in this covalent compound. So which prefix are we going to use? 2. So to complete this name, you're going to write carbon dioxide. So that di represents the 2, which means there are 2 oxygens, and we attach it to whichever element it coincides with. Pretty easy. So let's try another one. Let's do this. N2O4. So again, covalent compound, 2 nonmetals. Prefixes are going to be needed. So this is what? Nitrogen. Then we have oxygen again. Now, if we look at our compound, we see that there are actually 2 nitrogens. So we know we're going to be using the prefix di for nitrogen. And we have 4 oxygens this time. So tetra for oxygen. We have everything that we need to fully name this. So we have, I already forgot, dinitrogen, tetraoxide. How do you guys feel on this? Is there anything confusing about it? Or is there like something you need me to explain again? So I'm gonna have you guys do one on your own, and I want you guys to tell me what you guys get. I'll leave this up as an example. So I need you guys to give me the name for 17. So Street Fighter 6. I mean SF6. I'll give you guys a couple minutes, and then I want you guys to give me the answer. All right. Do you guys have an answer for me? What did we get for number 17? So the answer should have been sulfur hexaoxide. So one thing to note about the sulfur is that there is actually a one here. So if there's an element on its own, it's understood to be one. And it it said that one uses the prefixes of mono. However, we don't really use mono that much. You can if you want. It's not the wrong answer. So if you said monosulfur hexaoxide, that's correct too. But most of the time, mono isn't primarily used. Two through two through so on, it's obviously used. So that's just one interesting thing about nomenclature. So let's do one more. Do another one from your examples here. Let's do number 14. I409. So again, I'll give you guys a few minutes and then we'll go over the answer. Okay. What do you guys think the answer is? You had to take a guess. So we have four iodines, which means we're gonna have a prefix of tetra in the name iodine. We have nine oxygens. IDE at the end, and that's the answer. Let's go into another rule here. Let's go back to ionic compounds. So let's look at a lot of these. So a lot of these have more than like two elements attached to it. So this is because these metals are actually bonding with polyatomics. So if you go into your packet here, you get a long table of just common polyatomic ions. This is where things get tricky, and a lot of students tend to mess up. So it's probably best to pay attention here. So again, we're not using prefixes because we're not working with covalent bonds. So let's look at this first one here. We have BaCr4. Actually, I think I'm getting ahead of myself. Let's look at a polyatomic itself on its own. Let's look at nitrate. So nitrate is written like this. It comprises of one nitrogen and three oxygens. Notice the charge. So this compound, or this polyatomic, its total charge is -1. That means this comes as a package. Think of this as one thing, not four. And let's look at something like nitrite. So notice the only difference between the two is the oxygens. So this ends with ATE, and nitrite obviously ends with ITE. However, we can go a step further than this, as if we lose an additional oxygen, that means we're adding the prefix of hypo and keeping the same suffix of ITE. However, if we look at nitrate here and we add an additional oxygen, we're adding the prefix of PER, but keeping the same ATE. So again, notice that none of the charges change. They all stay -1, -1, -1, -1, -1. The only difference is the amount of oxygens. And this rule applies to most of these polyatomics. Of course, there's some that stand out that we can't really work with, like thiocyanate down here. No oxygens. So this rule doesn't really apply to it. But if you look into most of these, they have oxygens. And some already play that rule here. So if we look at hypochlorite, it has one oxygen. Perchlorate has four. So we can see that ClO2 minus would just be chlorite. And this one would just be chlorate. Does that make sense? Or is it confusing? How do you guys feel about this? As this is considered the trickiest or one of the trickier parts of nomenclature. Thumbs up, thumbs down. Okay. So knowing this in mind, let's try to name one. Let's name one that's in a compound. So let's look at this first one. BaCrO4. I think that S is a typo. So let's look for Ba in our periodic table. What is that? It's barium. CrO4 will be found in our polyatomics. This one. chromate. Let's name the compound barium chromate. One thing to know about polyatomics is that they do not follow the IDE rule. So whatever they're named, we're keeping that name. We're not dropping any letters from this polyatomic. And again, because we are an ionic compound, we are not worrying about prefixes. So one thing to know. However, one thing to understand is that polyatomics can be mixed with transitional metals. And like I said earlier, if we have a transition, we're going to be using Roman numerals to indicate the charge. So let's take a look at number 9. So this is obviously copper. CO3 is carbonate. However, if we look at our polyatomic, we know that carbonate comes with a charge A of 2 negative. So I'll write that down here. This is the charge of carbonate. Again, we want the charges to equal 0, and we know we have 1 copper here. So we can guess what its positive charge is, since transitional metals don't have a consistent charge on them, but by knowing the charge of the polyatomic, we can know what the charge of copper is. We have 1 copper and 1 carbonate. The carbonate is a 2 negative, so the copper has to be a 2 positive. So knowing that copper is 2 positive, which means we're going to be using a Roman numeral when giving the full name. So copper 2 carbonate. Again, things to note. 2 represents the charge of the copper. It does not represent how many coppers we have. And carbonate, we keep the ATE because it's a polyatomic. Any questions? Okay, let's try one more with a transitional metal, and then we can move on to the next roll. Let's try SNF4. Wait, that's not a polyatomic. How about MnF4? Wait, sorry. All right, that works. So let's see what we have here. Mn is manganese, and we know the manganese is a transitional metal, so Roman numeral and nitrate. However, this 4 here means we have 4 nitrates. So remember, think of this nitrate as one being. We know that the charge of nitrate is -1. We have 4 of them. Remember, we wanted it to equal to 0. So what is the charge of manganese going to be? We only have 1 manganese, and we want it to equal 0. So it has to be 4 plus. So we have all the information we know to name it. So let's name it. And that's it. So remember, transitional metal means Roman numeral, polyatomic, you keep the name. So let's move on to the next rule. Let's move on to acids. So let's go ahead and here. Numbers 19 through 22. So if we go to our sheet here with polyatomics, there's this phrase here on the side that says I ate organic apples despite them being poisonous. And the second saying is, my ride has hydraulics. And we notice that there are things underlined. So this is designed to help you memorize how the rules are played for acids. So let's try to visualize this saying here. So I ate organic apples despite them being poisonous. So what this means is I ate means if it ends in ATE on an acid, we are changing that ATE to IC. I ate organic apples. Furthermore, ITE, despite them being poisonous, means ITE is going to be replaced with OUS. I ate organic apples despite them being poisonous. And then this last portion here says, my ride has hydraulics. So if we keep following along, if it ends in IDE, the acid, we are adding a hydro prefix and changing the ending to IC. My ride has hydraulics. It's a little goofy right now, but it'll click here in a second. So let's put it to play. So let's take an acid, HNO3. One thing to know, we can tell if it's not stated that it's an acid, this AQ is a good indicator of that. AQ means the compound is in solution, and we often use AQ to indicate if it's an acid. So one thing to note for exam day. Let's see. HNO3. We know it's an acid because hydrogen is here. So acid, which leaves NO3. We know that's a polyatomic because it's in our chart here. So we know it's nitrate. Nitrate ends in ATE. So I ate organic apples. So the final name is just going to be nitric acid. Pretty easy. Okay, Let's take a look at another rule for acids. Let's look at number 19. So one thing to know about acids is that they have that hydrogen. This hydrogen is a positively charged molecule. And this polyatomic is a negatively charged. So when we look at our polyatomics, our PO4 here, phosphate, is a -3 charge. So for an acid to counterbalance that, again, equal to 0, this acid's going to need 3 hydrogens. So 3 pluses to counter this single 3 negative charge will give us 0. That's why acids have that hydrogen. That hydrogen is there to represent a charge, and it's also there to counter. It's there to balance the acid as a whole, because those polyatomics have a charge associated with them. So, knowing that, we can name this acid. Sorry. So this +3 and the hydrogen, it's going to come into play later on when you're made to do the reverse name. So let's name this one, number 19. So again, acid. So the hydrogen's an indication that we're working with an acid here. And this PO4 is a polyatomic. Like I said earlier, it's phosphate. So follow the rule again. We should have, if I can spell, phosphoric acid. So let's try to name it in a reverse. Let's start with the name itself and let's work backwards. So let's say we have phosphorus acid. Let's dissect the name here. We have the OUS ending. So now we're going to change that to ITE. And then we have this suffix, which we know it stems from our polyatomic. Oops. And we know it's this one because, again, the ITE was replaced with OUS. So we are working with this PO3, -3. Now remember, 3 negative. So because we're working with an acid, we're going to have hydrogens attached to this. And we know one hydrogen is equal to just a single plus charge. So as a whole, with all the information we have, we know that this is the final answer. Questions? Okay, let's move on. So that's it for acids. So let's move on to the next rule here. Hydrated compounds. So hydrated compounds follow the same rule as ionics for the most part. However, we're just adding one more thing to them, and it's this water. So when you see the hydrate, we're going to be adding, and we're going to be using the same prefixes from covalent bonds. So seven. Yeah, those are messed up A's. So again, the prefix is return. However, we are only going to be using prefixes to associate them with the water. That is the only time we will use a prefix when it comes to these compounds. So let's try to name one. So let's take FeCl3 with a water. So let's dissect this. We have an iron here. And we know irons are transitional metals. So we're going to be using the Roman numerals to represent the charge. So this is iron. And we have chlorine here. and we have 3 chlorines. We know that chlorine is a -1. And we have 3 of them. What is the charge of iron going to be? Again, we're working with 1 iron here. So that means its single charge has to be big enough to cancel these 3 negatives. So it'll be a 3 positive. So let's name this. Iron 3, again, Roman numeral, transitional metal, and it's the charge, not how many, chloride. However, we're not done here. We have this water. This water is attached to this compound. And we have 2 waters. And because we have 2 waters, we're going to be using di, because that's the prefix. And then all we're going to do is add hydrate. The hydrate indicates that the compound itself is being hydrated. So again, 2 means di, and the water is hydrate. Does that make sense? Is there anything confusing you guys so far? Or is everything making sense? Okay. Is there any rule you guys would want me to go over again? All right. So let's look at part 2 here. So for part 2, we're simply working backwards. So now we're given the name, and it wants us to write the formula down. All the same rules I've discussed so far still apply here. So again, we're working with covalence. We use prefixes. We're working with transitional metals. We still have the Roman numerals. IDE still ends as a way to mean stop. And if we scroll down here, we can see that polyatomics still keep their name. So all rules that I've discussed still apply. Now we're just working backwards. So we'll do a few more examples, and then I'll let you guys go to finish the page itself. So let's do like one or two from each section here. Oh, wait, we still have balancing equations. I completely forgot. So after balancing equations, then I'll let you guys. So let's do a ionic compound. Let's do number 3. Bismuth V chloride or 5 chloride. So that Roman numeral means we are working with a transitional metal. So we know where to look to find bismuth in the transitional metals region on the periodic table. Tricky. This is actually located in post-transitional metals, but it still applies here. Bi. And we know the charge for this is, ooh, that's funky. 5 plus. How do we know that? Roman numeral. Remember, Roman numeral means charge, not quantity. I know I'm saying that 1,000 times, but I have to make sure it sticks to your brain. And we have chloride. So again, notice the IDE, complete stop, and we're working with chlorine. We know the charge of chlorine is -1. Does that equal to 0? No. So we need more charges from chlorine to make it equal 0. So 5 plus, 1 negative. Now it'll equal to 0. So knowing this information, we can now write the formula. Bismuth and chlorine. Except we have 5 chlorines now. Pretty easy. What'd you guys say? Let's do one that involves a polyatomic. All right, I'm gonna erase this. Let's do number 9, potassium sulfate. So what's potassium in the element? What's the element? Potassium, a symbol, I mean. Can't talk anymore. It's K. And sulfate, we know it's a polyatomic because of the ATE. So sulfate is right here. So for with a -2 charge. So potassium has a +1 charge, right? We needed to make it equal 0. So let's go ahead and add another potassium here. 2 plus 2 minus makes 0. So take what we know. Because we have 2 of them, we have 2 on the potassium. Do you guys know where I got the charge on potassium from? Do you guys know why it's +1? Okay. If not, I'll do a quick refresher. Let's go to our periodic table. And let's look at potassium. 19. So let's get these groups. And I definitely recommend you guys writing this down in your notes. This first group, everything here is a +1. Next one, +2 charge. Transitional metals aren't given a charge. That's why when we name transitional metals, we rely on whatever they're attached to find the charge. So transitional metals are going to be inconsistent with what charges are associated with them, but that's okay. Halogens, this row 18 here, they're considered noble gases. So they are, in a way, quote unquote, perfect in a sense that they have no charge associated with them. So anything in this row here, 0 charge. Oops. The next row over, halogens, they're one removed from being noble gases. And because of that, they are actually -1 charge. Do you guys see a pattern here? Group 16, they are 2 removed. So these are negatively charged, or -2 charged. This little area is kind of a gray area. as things can get a little dicey, but it still applies the pattern. Another row over on row 15, we have 3 negative, and if we're coming from the metal side, boron is 3 positive. Carbon is a little tricky because it can be both positive or negative. But for this class, we won't get into the diciness of carbon when it comes to charges. But this is more or less the rules. This is how they're charged. So again, I would write this in your notes. If you printed out your packet that you use on the exam, I would write it down on the periodic table themselves. All right. I'm going to clear. And let's move on. Let's do covalent. And then we'll head to the next section. So let's remember covalence. We're going to be working with prefixes. So let me quickly write them down again. All right. Prefixes. So let's look at the first one. Carbon monoxide. We know the first part's carbon. C. Oxide. So remember the IE rule? That means something was dropped to be replaced with IDE, but we've done enough examples to know that this is oxygen by now. And mono. Again, mono means 1, but if we just leave the oxygen on its own, it's understood to be 1, as there's, well, 1 here. So a very easy one. Let's do one that's a little bit harder. It doesn't involve mono because it's boring. Let's do 17. Tetraphosphorus trisulfide. So tetra, we know, is 4, and tri means 3. And again, we're working with a covalent bond here. So 2 nonmetals. These are primarily just gases. So tetraphosphorus. What element is phosphorus? What's the atomic symbol for phosphorus? It's in the periodic table. P. Phosphorus is the letter P, or the element symbol P. And since it's has a prefix of tetra attached to it, P4. Trisulfide, again, IDE. So know that in the element sulfur, that last letters were replaced with IDE. And we're working with the prefix tri. So we have 3. Now remember, this is only with covalent bonds. This is an ionic bond, so no rules from there apply here. These aren't transitional metals, just strictly two nonmetals together. Do you have any questions? All right, let's go ahead and move on to the last part of this lab, and that is chemical equations, everyone's favorite. So I'm going to get rid of that. So in this class, we're going to be working with most of these chemical reactions. So let's go through each one. Combination. It's very self-explanatory. Two species are combining with one another to make one species. It's very straightforward. Next one, decomposition. It's more or less the opposite of combination. It's like decompose. You know, when something decomposes, it's being quote unquote tore in half, tore into pieces. So when we take one species and it's separated into two separate ones. Single displacement is when we start getting a little tricky in the naming. So when we have one species that's by itself and the combination species, when single displacement takes place, simply the single species is reacting with this one, the combination, to switch partners. So notice that the BC is formed into AC, and the B in that species is being pushed out. And then double displacement is more or less the same concept, except this time the two species are switching partners. So this AB is combining with the CD to make AD, and the CD is simply taking the B from the A. It'll make more sense when we actually use elements here in a second, but I'm just giving you the gist of it. Acid-base reactions is when, well, an acid and a base are put into solution and we get salt and water. That's really all there is to it. Again, from earlier, we know it's an acid when we have that H plus being attached to a polyatomic. And bases are more represented with OH. This is actually a polyatomic known as hydroxide, and it can be found in your sheet. But these two are associated with what they are. So H plus is often associated with an acid, and hydroxide is often associated with a base. Combustion, I know it says oxidation, but I like to say combustion. It's the same thing. It's when we take a hydrocarbon. Here it says it's simply a hydrogen and a carbon being together, and we add oxygen, and we'll get a direct product of carbon dioxide and water. I believe in the last lab, we actually did a combustion reaction, and I mentioned that combustion reactions, we're always going to have these three species. We're always going to get water, and we're always going to get carbon dioxide as a product. Excuse me. And our reactant is always going to be reacting with an oxygen. So now that we know that, let's go ahead and try an example. So let's do number 1. Iron reacts with oxygen to form iron 3 oxide. This is why nomenclature was very important in the beginning, because if you don't know nomenclature, you don't know what any of this means. So let's follow the sentence. Iron reacts with oxygen to form iron 3 oxide. We know that the charge of iron is 3. And we know the charge for oxygen is 2. In this little trick, we simply cross multiply to get us this. Do you guys know how I got that? So again, iron 3 is the charge. Oxide we know is oxygen, which has a charge of 2 negative. And I just realized my typo here. That's why it looked funny. So this is still the same kind of math that we did in nomenclature earlier. We want them to equal 0. So we were going to need 2 irons, 3 oxygens, because this gives us 6, and this gives us 6 negative. This equals 0. And we just simply count however many we have here. 1, 2, 1, 2, 3 to give us this combination. Why did that erase? So I hope you guys know how I got that. Is this correct? No. There's one thing missing. Oxygen is a diatomic. Remember? I believe this was in the first few weeks of class. The list of diatomics. So diatomics mean that there's in the natural state of this element, there's actually two of them. So are we done? Actually, we're still not done. Is this reaction balanced? No. We have one iron on this side and two irons on this side. One iron in the reactants and two irons in the products. So now we have to balance. Oh, let's oxygens. Two oxygens in the reactants and three oxygens in the products. So how would we balance this? So if we add a 2 here, that means now we have two irons on the reactants. We're still not done because the oxygens aren't balanced at all. So let's take a look. What if I add a 3 here? So because I added a 3 here, we're multiplying the oxygens. So now this is 6. We're still not balanced because now we only have 3 on the product side. So let's add a 2 here. Let's add a better 2 there. That works. Again, because iron 3 oxide is one species, this 2 is going to be multiplying to both of these. So now we have 4 irons and 6 oxygens. Still not balanced. So let's look at our iron here in the reactants. Let's multiply this by 4. Now it's balanced. So the final answer for this one would be That is the balanced equation for this reaction. So does everyone understand how we got here? Okay. Let's try decomposition. So let's do let's do number 5. Magnesium carbonate decomposes into magnesium oxide and carbon dioxide. So we know magnesium is a metal. Carbonate is a polyatomic. Found here. So CO3 2 negative. Magnesium oxide. You should know by now that oxide is an oxygen. Carbon dioxide. So let's put this into a chemical equation. Magnesium carbonate. Well, first we know the charge for magnesium is 2 plus, and the charge on carbonate is 2 negative. So these equal to 0 automatically. So no further work's needed here, which works out perfectly. It decomposes into magnesium oxide. Oxygen has a 2 negative charge. So another easy balance here. And we have carbon dioxide. Carbon dioxide, as we know, is a what? Covalent bond. So we don't have to worry about charges here. And we know di means 2, so dioxide. Is this balanced? Well, let's take a look. So we have magnesium, carbon, and oxygen. We have one magnesium on the reactants, one magnesium on the products, one carbon here, another one carbon here, three oxygens here, and then we have one oxygen here with the magnesium oxide, and two oxygens here with the carbon dioxide, which gives us a grand total of three. So this one came balanced already. Pretty easy, thankfully. So let's move to single displacement. I guess, do you guys have any questions so far? No questions? All right. Let's do number 9. Chlorine glass, chlorine, oh brother, chlorine gas reacts with sodium iodide. Wow, that's not sodium. I guess I am running on fumes now. Okay, so one thing to note is we're only given one half of the reaction. So let's put it into play here. Chlorine gas and sodium iodide. Chlorine is a diatomic. So in its natural state, there's going to be two of them. Diatomic, di means two. Now we have sodium iodide. Sodium is a plus charge, single plus charge, and iodine is a single negative. So this works out. Zero charge, zero total charge, I mean. So now let's see what our product's going to be. So remember, single displacement means that we're switching one partner for another. Remember how the B and A switch? Same concept here. Now we're working with elements. So the metal is going to want to react with a different non-metal. So we get a product of sodium chloride and iodine by itself. Yeah, see how I got that? And again, iodine is also a diatomic. So now let's balance. Sodium, iodine, and chlorine. So we have two chlorines here on the reactants, one on the product, two iodines in the product, one in the reactants, and one sodium in each side. How would I balance this? I would add a 2 here. Excuse me, 2 sodiums and 2 chlorines on the products. So in terms of the reactants, I would add a 2 here. Which changes a reactants to have 2 sodiums, 2 iodines. And now we are balanced. And that's a single displacement. Now let's make things trickier by working with double displacement. So let's do 18. We have, oops, zinc chloride reacting with ammonium sulfide. So ammonium is not on the periodic table. It's actually a polyatomic. Here it is. It's the second one. So NH4 and sulfide. Much like a single displacement, we aren't given what our products are. That's okay. So let's look at the zinc chloride first. Is that balanced? Well, we know the charge for chlorine is -1. So what's the charge of zinc? Zinc is a transitional metal, and we're not given a charge here. So if it's a transitional metal, in this case, and there is no parentheses, it's the same as saying 1. So zinc chloride here, same as zinc 1 chloride. Because you guys are starting to notice how little 1 is written in chemistry. So yeah, zinc chloride is balanced. Ammonium sulfide. So we know sulfur is a 2 negative, and ammonium is a positive. Is this balanced? No. So we actually need a second ammonium to indicate that it's balanced. Now we're going to try to find our products. So because it's double displacement, it's easy to just say that the positively charged are going to switch with each other. What do I mean by that? So the zinc is going to switch with the ammonium to get zinc sulfide, and the ammonium would be the vice versa. So we have NH4Cl. You're never going to have positives and positives together in double displacement, or negatives with negatives. So it's always plus minus plus minus. So is this balanced? No. So let's balance it. We have zinc. We have chlorine. We have sulfur and ammonium. So because it's a polyatomic, we can actually keep this as one species here. And it's actually going to be useful because it'll make our work less cluttered. So let's balance. 1, 1, 1, 1, 1, 1, and 2, 1. Oh, wait, I skipped this stuff. Our products balance. So zinc sulfide. So we know zinc is +1 from earlier. Sulfur is 2 minus. I mean, we're going to need 2 zincs. Ammonium is a +1. Chlorine is a -1. And that stays balanced. So we actually have 2 zincs on the product side. So I would add a 2 here. And now I would add a 2 on the products. Now it's balanced. Simple, tricky, both. So this is double displacement. So more or less an extra step compared to single displacement. All right. Let's move on to the last two. So acid-base reactions. So if you scroll up, we know that with an acid and base, we're always going to get water and we're going to get a salt. The salt is a little tricky, but I'll show you guys what I mean in a little bit. But for now, we know that water is 100% going to be a product of an acid-base reaction. So let's see. Let's do number 19. It says we have sulfuric acid reacts with ammonium hydroxide. So sulfuric acid. Let's take what we know from nomenclature to decipher what that is. So sulfuric, we are working with IC. So I ate organic apples. So that IC is going to be replaced with ATE. And we are looking for sulfuric acid. So we know we're going to be finding sulfate. So SO4. Actually, I'll write it up here. SO4. It's a 2 minus. And since we're using an acid, we're going to have 2 hydrogens to balance the 2 charge. Reacts with ammonium hydroxide. So we just worked with ammonium, so we know that that's NH4. And hydroxide can be found in our polyatomics, which is OH minus. And we know we're going to get water. Because again, we are working with acid and base. We have our acid. We have our base. Now we just need is salt and water. So our salt is actually comprised of a positively charged and a negative charge. So our salt is going to be comprised of our ammonium and our sulfate. Again, ammonium is one positive charge and sulfate is two. So we're gonna have two of them here. This is our salt. It kind of looks like a double displacement. And in a way, it more or less is. The reason we get water is because this hydroxide is actually being is reacting with the hydrogens from the acid. And when you mix those two, you actually get water. I mean, water in theory, right? Not going to be drinking this thinking it's just normal water. But let's balance this now. So we're working with a lot of polyatomics here. So let's have, we know we have hydrogens. We have oxygens. We have nitrogens and sulfurs. So let's count. So we have 2, 6, 7 hydrogens. We have a single sulfur for 5 oxygens and a single nitrogen. And on the other side, we have 1 and this 2 here distributing to both sides. So we have 2 times 4 is 8. So 8 plus this 1, 9. And then for oxygens, we have 1 here, 4 here. So a total of 5. Nitrogens, this 2 is being distributed to the nitrogen and ammonium. So we have 2 here and a single sulfur. It looks like a lot, but maybe it's not. We'll see. Where would I go first? Well, for starters, I'll put a 2 here because we know we need 2 nitrogens in the end. So this is going to multiply to all of these. So 2 nitrogen, and we have 2 times 4, which is 8, plus the additional 2 from the acid gives us 9. And then the oxygen. So we have 2 oxygens now, plus the 4 from the acid, which gives us 6. So now let's look at our products. Hmm. could put a 2 here. Two times 4. 2 times 4. This is 4 hydrogens plus the ones from here gives me what? 2, 4, it's 8 plus it's 12. And then in terms of oxygens, we have 2 plus the 4, 6. Did I count my hydrogens right? 2 here, 8, 10. Oh, I did. This is supposed to be 12. I forgot to count the acid ones. So 2 times 4 is 8, plus an additional 2 makes 10, plus the 2 from the acid gives me 12. It looks like a mess. I'm sorry. I hope you can follow that. Oops. Did, did I lose you guys? Did I confuse you? Do you get how I got everything? Well, it's balanced. Any questions about the acid base? I think acid base might be on the harder side, but luckily there's only, well, 2 left. But just remember how the salt was made, plus and minus, and the OH and the H is reacting to get water. All right, let's move on to the last. We're almost done. Combustion reactions. So, like I said earlier, combustion reactions consist of having a oxygen in the reactants because you need oxygen to make fire. And after that fire is produced, carbon dioxide is being released, and so is water. Now let's take a look at an example here. Let's do the first one, 22. So we have combustion reaction for propane, and it gives us what propane looks like. So C3H8. And like I said, combustion reaction, we need oxygen in its natural state to create a combustion. And of course, we know that our products are going to consist of carbon dioxide and water. So all that's left is to balance the equation. So we have carbons, we have hydrogens, and oxygens. That's all we're working with here. We have 3 carbons in the reactants, 1 in the product, 8 hydrogens, 2 hydrogens, 2 oxygens, and 3 oxygens in the product side. So how do we do this? How do we go about this? I don't know. Me personally, I would start with a 3 here. That'll give us 3 carbons. The 3 gives us 6 plus the 1 here, which gives us 7. Hmm. How about that water? We can add a 4 here to give us 8 hydrogens. And 4 times the single oxygen gives us 4 plus the 2 oxygen here. This makes 6. Remember, this 3, can't forget about it. Multiplying it gives us 18. 18 total oxygens. If I do my math right. 3 times 2 is 6. Oh, I did my math wrong. Jump the gun here. Oh, let's retry this. So we know we have 6 here because of that 3. And the 4 from the water is giving us 4 here. So in reality, we actually have 10. Oops. So we're almost there. And now we just need our oxygens to be balanced. Thankfully, we could just put a 5 here. 5 times 2 makes it 10. Now it's balanced. So this one was a little tricky. Well, it was tricky for me because I don't know how to multiply. That's okay, because you guys know how. So that's combustion reactions. Again, we know it's combustion because we have oxygen needed to make carbon dioxide and water. And that's it. I think I gave you everything you need to know to do this entire page. Looks like it's due next Wednesday. If you still need help understanding these concepts, Angelia and Dr. Henry have labs this week. They're going to be covering this again. I believe Dr. Henry's actually covering this in lecture as well tomorrow. So there's more help there. And just another reminder that tomorrow your practice exam goes live. Saturday, your second exam goes up, and you guys have a week to get that done. And that's it. That's all I have for you today.